Hello, and welcome to lesson 11 of this Introduction to Linear Algebra with Wolfram U. The topic for this lesson is the LU factorization. So let's begin with a brief overview of the lesson. So the goal of this lesson is to express a square matrix A as a product of two simpler matrices, which I'm going to call capital L and capital U. Now, the letter L over here refers to what we would call a lower triangular matrix, while the letter U refers to an upper triangular matrix. So that's what is called an LU factorization. And here's a simple example. So you have a matrix A, and I'm going to define two more matrices L and U. Notice that L has got zeros above this diagonal and U has got zeros below the diagonal. Now, it turns out that with these definitions, A is the product of L and U. So let's see over here, if we do L dot U, you do get back A. So that's the idea of an LU factorization, and this factorization can be used to solve linear systems of equations in a very convenient manner. So just to motivate the lesson, let's first talk about lower triangular matrices. So here I have a linear system. It's a very special kind of linear system. It looks kind of triangular. And if you look at the coefficient matrix for a system, so you have 1, 0, 0 from the first equation. You have 3, 2, 0 from the next one, and 1, 2, 5 from the third one. So that is a lower triangular matrix because all the entries above the diagonal are 0. Now, if I want to solve the system with linear solve, what I would first of all do is to define the matrix right hand sides vector, which is B. So B is 2, 8, 19. And then I solve linear solve, and I get back 2, 1, 3. Now, of course, in this case, you could have got x, y, and z directly because x is 2 clearly from here. And if you plug back x is 2 over here, then you get back y as 1. And if you plug back both those in the third equation, then you get back z is 3. So that's a really simple system to solve by hand using forward substitution. Now, at the other end, you have upper triangular matrices and upper triangular systems. So here is an upper triangular linear system, which has got just the opposite shape. And the coefficient matrix over here is 1, 1, 5. And then you have 0, 3, 2, and 0, 0, 1. Okay, now that's an upper triangular matrix because all the entries below the main diagonal are 0. So when you want to solve it with linear solve, you first of all set up the vector B over here, which is 13, 8, 1. And then you have linear solve giving you 6, 2, 1. But of course, the 1 could have been guessed from here itself. And once you have the 1 over here, then it can work out the value of y, etc. So this is a very easy system to solve by hand using backward substitution. Okay, so with that background, we can now define the notion of LU factorization. So I'm going to assume that the matrix is invertible, it's non-singular. And in such a case, we have an LU factorization if it can be written in the form A equal to L dot U, where L is lower triangular and U is upper triangular. Now, the point is that, as we'll see, these matrices L and U can be obtained by using row reduction. But sometimes you may need to permute, you might need to interchange some rows of A to get the factorization. Now, just like in the factorization of numbers, you may or may not have uniqueness. In fact, generally don't have uniqueness, so you should not expect to get exactly the same answers from everywhere for L and U. Fortunately, we have a very nice function in the Wolfram language called LU decomposition, which can be used to obtain an LU factorization for A. Okay, so now let's take an example where we try and do the LU factorization with row operations. So here is a matrix A, just 2 by 2 matrix. And I first of all want to make this 3 into 1. So I multiply the first row by 1/3. Okay, so there it is. I'm trying to get 1/3. So I basically take the elementary matrix with a 1/3 over here, and then I get back a simpler matrix with a 1 over here. Then I want to make that into a 0. So I set up an elementary matrix and I obtain the matrix U. And now that looks right. So basically, by just some row operations, we got the matrix U. Question is, how to get the matrix L? Well, the matrix L can be obtained by using the inverse of those operations. So the matrix L is the inverse of E2 dot E1. You get that over there, and then you verify the answer, and you do get back true over here. So that's the way you'd obtain the LU factorization with row operations. But like I said, fortunately, we do have a nice function which can do that automatically. So here is a 3 by 3 matrix. I give it to LU decomposition. And notice that I've written the answer as a list of 3 elements. The first one called LU, the second one called P, the third one called C. Okay, now to obtain L and U, what you do is you examine LU, and I want to kind of split this up into L and U. So what I do is I kind of want to pick the lower part of it and then the upper part to get the L and U. So here's the operation of doing that. And what that does is basically it takes the lower part over here and then adds ones along the diagonal. That's what's happening over here. And then I can also upper triangularize the matrix with another function. And now I've got the matrices L and U. So that's lower triangular, that's upper triangular. And if I want to check the result, I first of all need to look at P. So the P over here tells me that in this case, there's no change, no interchange done to get the factorization. So L dot U is A with the same order. Now, the C over here is actually a number called the condition number. But that only matters if you have decimals or inexact quantities in your input, and it turns out in this case it's just 0. Okay, so now the question is, what does the vector P mean? So here's a matrix A, and you see you got a 0 over here. That's a problem because you cannot hope to get the LU factorization straight away. So if you try to do LU decomposition over here, that's the LU part. I get the matrix L. I get the matrix U. Now, the permutation vector P in this case is 2 and 1, because basically what you do is you just flip those two to get the 0 down. And once you've done that, in fact, your L is very simple. It's just 1, 0, 0, 1. And so the U over here is just a kind of flipped version of the matrix A. So if you do L dot U, you do get back the correct A over here. Right. Well, you're almost there because you still need to do the permutation. So I do that, and then I get back true. So the point over here is that the permutation vector P actually tells you what to do to the answer over here to get back A. Okay, and the condition number C over here is still 0. Okay, so finally the condition number, the C. So here I have a slightly larger matrix, but now it's got decimals, it's got real number entries in exact numbers. And if I find LU factorization, let's not worry too much about the L and the U, although they do look correct over here. I don't worry too much about the P because it's possible the rows will interchange along the way, but now the condition number is no longer 0 because you actually have inexact numbers. So condition number tells you, roughly speaking, how much problematic the calculation would be at a later stage. So now you know what the LU means, what the P means, and the C means, and we are ready to apply ideas to solve a linear system. So here is a linear system AX equal to B defined by a matrix and a vector. I compute the LU decomposition. Here's the L, here's the U. I check the answer, Nothing's much changed over here. Now what I do is I first solve the system L y equal to b. Notice I've put the permutation vector over here just in case there was some interchange that might be necessary. Then I do the second part, the ux equal to y, the upper triangular part, and now I check, I get back just the same answer with linear solve. So point is, you can now do your linear solve in two steps, the kind of the L step and the U step. But what you get back is the same answer either by doing it in the two-step method or by using the direct method. So that's how one would use to solve a linear system with the LU factorization. And that brings me to the end of the lesson. So in this lesson, you learn to factorize a non-singular square matrix as the product of lower and upper triangular matrices. So this factorization is called an LU factorization, and we have a very nice function which does it for you automatically. Okay, the point is that this factorization actually gives you a very efficient method for solving linear systems. So in fact, this is why LU factorization is very important in linear algebra. And in the next lesson, we'll talk about determinants. But before that, do review today's lesson. It was quite advanced and complicated because we have this new notion of factoring matrices, not just multiplying them, but actually factoring them into simpler parts. And that's a very useful operation in linear algebra. So I'll stop over here. Thank you very much.